Have you ever imagined what would happen if all the bearings in the world suddenly vanished? Without them, Shinkansen trains couldn't race along the tracks. Charles Leclerc couldn't win a championship, and countless rotating mechanisms across the globe would grind to a halt. Behind so much of the motion around us lies a tiny component that most people never even notice: the bearing. So, how are the bearings that keep our modern world moving actually manufactured? Join Mido Explained as we explore the entire bearing production process inside a factory. The idea of bearings dates back more than 2,000 years. Archaeological evidence suggests that the ancient Romans used wooden balls or rollers to reduce friction when moving heavy objects. However, modern bearings did not truly emerge until the Industrial Revolution in the late 19th century, when machines began operating at much higher speeds and carrying much heavier loads. In 1883, German engineer Friedrich Fischer invented the first machine capable of grinding steel balls with almost perfect precision, laying the foundation for the modern bearing industry. Since then, these small components have become essential to almost every rotating system. From car engines, high-speed trains, and industrial robots to jet engines and giant wind turbines. How many devices in your home do you think use bearings? Let us know one that you're sure contains bearings in the comments below. Every bearing begins as carbon-chromium steel, a material prized for its high hardness and excellent wear resistance. For a medium-sized bearing, the process starts with long steel bars, roughly 3 inches in diameter. These are fed into a cutter that slices them into short billets, each about 2 inches long, containing just enough steel to form a set of bearing rings. The billets are then passed through a furnace and heated to approximately 2,000 degrees. Once the steel is glowing red and sufficiently malleable, a high-pressure forming press punches out the center and separates the material into 2 nested steel rings. The outer ring forms the housing, while the inner ring sits at the center and will eventually encircle the rotating shaft. The space between these 2 rings is where the steel balls will roll. However, the rings are not yet hard enough for long-term service. They are conveyed, either in batches on trays or in a continuous stream through a heat treatment furnace, where they are heated to about 1550 degrees, rapidly cooled, and then tempered. This process hardens the steel and enhances its wear resistance, preparing the rings for the precision grinding stages that follow. After heat treatment, the steel rings are extremely hard, but lack the precision required for assembly into bearings. They are transferred to automatic grinding machines, where high-speed grinding wheels remove minute layers of metal from the surface. First, the inner bore of the inner ring, the part that will eventually fit around the rotating shaft, is ground. The steel ring is held and continuously rotated while the grinding wheel advances into its interior. Depending on size and specifications, a grinding cycle on a mass production line can take anywhere from a few dozen seconds to a few minutes. Automated measurement systems continuously monitor dimensions and can adjust the grinding depth in real time during production. Next, the outer diameter of the outer ring is ground, followed crucially by the raceways on both rings. The grinding wheel is dressed to match the specific curvature of the raceway. The machine then slowly removes a tiny amount of material until the raceway achieves its precise design shape and dimensions. However, grinding is not the final step. The raceways undergo a super finishing process, utilizing ultra-fine abrasive stones or finishing tools that oscillate against the rotating surface to remove any remaining microscopic irregularities. This process can reduce surface roughness to approximately 0.1 micrometers Ray for high-precision bearing surfaces. Throughout the grinding process, a large volume of oil and coolant is continuously sprayed onto the workpiece surface. This not only dissipates heat, but also flushes away steel chips and grinding dust from the cutting zone. Instead of being discarded after use, the oil and coolant mixture is filtered to remove metal particles and then recirculated into the production line. This solution reduces production costs while maintaining consistent machining quality. Finally, each steel ring is measured and sorted according to tolerance specifications before proceeding to assembly. This ensures greater precision when fitting together the inner rings, outer rings, and balls. Precision in individual components tells only half the story. A bearing's performance also depends on how those components are assembled. First, the inner ring is offset to one side of the outer ring, creating a gap large enough to insert the balls between them. Depending on size and design, a standard deep groove ball bearing typically holds between 7 and 12 steel balls. On automated lines, the balls travel from a hopper down a feed chute. A machine counts them precisely and pushes them one by one into the gap. For smaller production lines, specialized products, or semi-automated assembly processes, this step may also be performed manually. Workers offset the inner ring, insert the balls into the gap one at a time, and verify the count before realigning the inner ring to the center. Next, a tool or mechanism spaces the balls evenly around the circumference. Once the balls are correctly positioned, the cage is installed. It does not lock the balls in place, but creates individual pockets that maintain the spacing between them while allowing them to roll freely. In the case of a pressed steel cage, the two halves can be positioned from opposite sides and joined together. After this step, all the balls are held securely in place and prevented from clustering on one side. The bearings proceed to the automatic grease dispensing machine. A nozzle injects a preset amount of grease into the space between the rolling elements, raceways, and cage. For small and medium-sized sealed bearings, each unit may require only about 0.5 to 3 grams of grease, depending on size and design. The dispensing machine controls each injection with high precision, ensuring that the products receive a nearly uniform amount of grease. It is important that the bearings are not completely filled. In many applications, the initial grease fill occupies only about 30% of the internal free space. Finally, the bearing is sealed using rubber seals or metal shields on one or both sides. A machine feeds each seal or shield into position and presses it into the groove on the outer ring. Seals offer superior protection against dust and contaminants, but typically generate more friction, whereas metal shields produce less friction and are suitable for high-speed applications. Once the second side is closed, the balls, cage, and grease are secured inside, forming a complete sealed bearing. Before leaving the production line, a laser marks information, such as the product code, dimensions, or manufacturer's symbol, onto the outer ring, facilitating product identification and traceability during use. Before leaving the factory, every bearing must pass a final series of quality inspections. The process begins with an automated dimensional inspection system which measures each bearing and sorts it into the correct tolerance class to ensure every component meets the required design specifications. Next comes one of the most critical tests: noise and vibration inspection. The bearing is spun at a controlled speed, while highly sensitive sensors detect tiny vibrations and sounds that are almost impossible for the human ear to hear. Even a microscopic scratch on the raceway, a single particle of dust left inside, or a dimensional error of just a few micrometers can produce abnormal noise during operation. Any bearing that fails to meet the required standards is immediately removed from the production line. Only those that pass every inspection are approved for shipment. This rigorous quality control is what allows modern bearings to operate reliably through millions of rotations, whether inside everyday household appliances or highly demanding industrial machinery. The completed bearings are sorted, packaged, and prepared for shipment to markets around the world. The United States is one of the major destinations where these bearings are installed in cars, electric motors, industrial machinery, and countless other mechanical systems. Interestingly, although many bearings look almost identical from the outside, each type is engineered for very different operating conditions, including specific load capacities, rotational speeds, and working environments. That's why choosing the right bearing is just as important as manufacturing it with precision. Only when both come together can this small mechanical component operate reliably for years inside the machines that power the modern world. Few people realize that behind a small bearing lies a manufacturing process measured in micrometers. Which part of the bearing manufacturing process surprised you the most? Let us know in the comments below. And if you enjoy exploring how things are made inside modern factories, don't forget to like this video and subscribe to Mido Explained for more fascinating stories behind the world's most incredible manufacturing processes.